and then Samsung Exynos processors had for a long time had perceptron predictors in them. My entry is based on multi-perspective perceptron prediction. I combine it. Andre is disappointed to find out that I actually used Tage. He wanted, which is before the talk. He was saying, "Oh, something without Tage," but no, it has his Tage SCL, the one that was provided by the organizers. I thought, okay, just leave it in there and use the 128, as Rami suggested, use the 128 kilobytes for something else. I applied some optimization. MPP is optimized to complement Tage SCL, so I developed MPP knowing that Tage SCL will be there, so they're not developed independently. I applied a nonlinear transfer function for MPP, also for the perceptron component of Tage SCL. The outputs of MPP and the SC component are combined to produce the prediction, and the way the outputs are combined is specialized for MPP and Tage predictions and the Tage confidence. So I'll have a little combiner. I put a little bit of thought into to come up with a combination. We have Bloom filters for always taken, never taken branches, so that those will be predicted easily without bothering the prediction tables, because there's no BTB in Rami's framework. One of the things he talked about, and they should do that, they should put a BTB in the framework because real processors have BTBs. We also speculatively do table updates based on the prediction, not the ground truth, and roll back those updates on misprediction, and that helps improve accuracy a little bit. So Tage by itself is limited. It uses only global history. It has to use history links with a total ordering in order to choose the longest match. This graph shows for this year's traces sorted by MPKI that Tage and MPP with global history only, which is like a big OGL, I guess, with evolved history links, they get about the same accuracy, more or less, and it's not good compared to what we know we can get done. Perceptron is essential to accuracy. So this graph shows when we add the perceptron component, either through the SC of Tage SCL or through my predictor, the MPP, we get better accuracy. So we'll get, instead of the 3.8 something range, we get 3.5, 3.4 something range by adding the perceptron component. Perceptron can use multiple kinds of history beyond global history, local history intervals, rather than starting at 0, you can start at 4 or 16 or whatever. Tage can't do that. Tage SCL combines Tage with perceptron using multiple kinds of history. Don't build a processor today with Tage only, because you'll get poor accuracy. You need something else additionally, and perceptron is a good thing, and it's not hard to build. The multi-perspective idea is, rather than just use global local history, use many features, or sort of multiple perspectives on branch history. It's a hash perceptron, like most perceptron predictors these days. It sums weights indexed by hashes of features and updates those weights using perceptron learning. And the contribution of the MPP idea is a wide range of features. There's traditional features like global history, path history, local history, combinations of them, and the bias. If a branch has a bias, that's also an important component that tells you what the branch is going to do outside of any correlation with any other feature. And then novel features, the innermost loop iteration counter, which has been talked about a great deal today. Andre had a version of it. I had an alternate version that I came out with in the last branch prediction contest that turned out to work better for those traces, works better for these traces too. I tried both of them, and the forward Emily works best for these traces. And then there's some other novel features that I described 9 years ago. I'm sure none of you remember, some of you weren't even born, but it was, you can read about them. Modular history is my favorite one. It tries to solve the problem of misaligned branches. When you have branches in the global history that sometimes are there and sometimes are not because they're skipped over, modular history tries to address this problem by dedicating multiple tables to different sort of slices of history that ignore certain PCs to avoid that problem. And it turns out to provide a nice boost. Other stuff, a similar idea for PAT. I'm trying to speed through this so we don't go over time. And I already talked about this a million times in other forums. Recency position is one of my favorite. The idea is you keep a recency stack of recent branch PCs, and then go look up, when you want to predict a branch, go look up what's the position of this branch I want to know the prediction for. What is the position in this recency stack that's managed by LRU? And that position is used as a feature to index into a table. And that turns out to have a nice correlation with the branch outcome. So we use that and get a little boost. Blurry path, this is something that's just sort of, you can think of it as like the page history, which pages have we visited for different page sizes. And that gives you an idea of where we came from rather than the precise branch history. And that can sometimes lead to improvement. This is another one that you can read about, Tage. So this is a new one. What was the outcome of the Tage predictor? That's unrealistic because that means now I have to do them sequentially, but it turns out to be a pretty good estimate of what the branch is going to do. And so we use a combination of Tage prediction and Tage confidence as another feature to index the Perceptron predictor. To make the prediction, the features are computed, hashed, exclusive ordered with the PC. The resulting index selects a weight from a table. The weights are summed and then thresholded to make a prediction. The weights are updated with Perceptron learning. Some optimizations, again, filtering always or never taken branches from updating the weights table. So if a branch is always taken or if it's never taken, then the only thing it's going to do is pollute the branch prediction tables. So we just say, predict that it's going to do what it's always done. Also apply a sigmoidal transfer function to weights before summing. That turns out to provide a surprising amount of extra accuracy. We adapt the threshold training from Andre's OGEL paper. This is the same I was doing 9 years ago. And then features can choose different hash functions. So each feature might have a different hash function for a little bit of extra accuracy, a little extra distribution of accesses across tables. What else? To search for features, I use a genetic algorithm to find a rough cut, pretty good candidate, and then finished it off with hill climbing. I used a fast simulator with traces extracted from Rami's simulator. So instead of spending about 8 hours for the full out-of-order simulation, I'll spend about 30 minutes just to simulate the branch misprediction. So I'd ignore all this stuff, that the pipeline, the delays, and then cycles, and just look at branch prediction accuracy. The set of features and parameters are represented with a binary encoding. I start a population with thousands of random sets of features. Crossover and mutation provide the initial rough cut, and that best candidate is optimized with hill climbing and small tweaks like change this history by 1 or 2. The final set that you can read in my source code has 33 features, 8 different local history features, several combinations of global history and modulo history, and just global history features with modest history lengths. The forward IMLI that I was talking about, the recency position with a stack depth of 56, that turned out to be the magic number for the most accuracy, and it has a Tage feature. I like this nonlinear transfer function. I think you should do this if you're building a branch predictor. And if you want, I can tell you how to do it in a realistic way. It maps weights so the weights are 6 bits. And I reserve negative 32 as a special value. So from negative 31 to 31 to negative 255 to 255. It's implemented in my code with a lookup table. I found this weird function with a genetic algorithm seeded with randomly chosen piecewise linear curves. It fits a so-called rational function of 3.2x divided by 1 minus x squared divided by 1,000. The curve fitting software told me that. And that's about what the curve is. I tweaked slightly some of the values near the origin to get a little bit extra accuracy. But what it does is it emphasizes the larger values. So the smaller values aren't counted for as much in the final summation, and the larger values are counted for more. And that helps the Perceptron Predictor make more accurate predictions by a lot. To combine it with TageSCL, I pretty much left TageSCL alone, except I applied this transfer function also to the statistical corrector. But the final prediction for my predictor is a linear combination of MPP and SC confidences. The slope and bias of these linear combinations are tuned per combination of MPP prediction, TageSCL prediction, Tage-only prediction, and Tage confidence. That gives me 24 sets of slopes and biases, most of which I tuned individually, and that helped a little. There's an additional bias term that's dynamically determined to minimize the number of recent misses. So it looks at which bias term would have minimized recent the misprediction rate recently, and then chooses that for the next prediction. So there's 64 possible biases tracked with 3-bit counters for each of the 24 combinations. So it's a compact little thing that combines TageSCL and MPP predictions. How to filter always never taken branches. The right way to do it was with a BTB, but since they don't have a BTB, we used 24 kilobytes worth of the 192 kilobyte budget to 2 big-ass bloom filters. Taken branches are inserted into one filter, not taken branches are inserted into the other, and if something appears in only one filter, then it's either always taken or it's never taken. Branches only update the MPP tables if they appear in both filters, but most branch histories continue to be updated even for always taken and never taken branches, because they provide a rich context that the branch predictor can use to pick on correlations with path history. The prediction is based on the filter that has the branch, or a hacky static prediction if it's an as yet unseen branch. So we have a sort of static predictor that predicts the outcome of a branch on the very first access. The filters are unrealistically wasteful of a hardware budget. In a processor with an 8K entry BTB, I would only need 1 kilobyte of additional state to track always taken and never taken branches. But I have to do this. I have to do this filtering because MPP is more vulnerable to aliasing than Tage due to updating all the tables. So the filtering is nice. Tage updates maybe a couple of tables. MPP updates all the tables, and so there's a lot more aliasing. So I really need to get rid of anything that needlessly updates the MPP tables. This is where the value of these optimizations come in. The graph shows the MPKI when a given optimization is removed, and that tells you how valuable that optimization was. The most valuable optimization is the filtering of those always taken, never taken branches. That when I take that away, that increases MPKI by 0.14. The nonlinear transfer function, if I get rid of that and replace it with just a scaling from negative 255 to 255, that's linear, I get an increase of 0.06 MPKI. So that helps something. Dynamic bias tracking, that additional component for combining the two predictions, if I get rid of that, it's plus 0.042 MPKI. Speculative table update, I thought that would buy more, but it gets something that gets 0.033. Tuning the slopes and biases just took a lot of computing time and only helps plus 0.026. I'll leave it in there. And so this average MPK is computed over all the categories. What else? So this is a table of. So this is not the organizer's weighting function. This number isn't directly comparable to the numbers that comes out of the simulator. I don't even know if I have that in this presentation. Maybe I do. It's in the final paper. So this is unweighted over all the 110 traces. This is pretty much saying the same thing as that graph was. Optimized for MPKI rather than IPC, and I was thinking that maybe optimizing for IPC would have been a better idea, but according to Rami's remarks this morning, maybe it doesn't matter. Their speedups are kind of low. I don't know about their simulator. I expect better speedups for the improvements I saw in MPKI. computation of the hardware budget, which is, you can find in the paper. What else? So the predictor is unrealistic because I'm going purely for accuracy, just as Andre said in his talk. There are ways to make it more realistic. Limit the number of tables. We can, that cuts down the selection logic and the adder tree. Replace the taken not taken history with hashes of bits from taken branch PCs and targets, so we can update history on taken branches. It's a trick that people know that they should play. Avoid the sequential step of the transfer function. Right, I say I want you to look up something in a table before you go look up something else in another table. We can fix that by applying the transfer function on wider counters during the update stage rather than during the prediction. That just costs more hardware. Think of less hacky, more efficient bias tracking algorithm. Head pipelining to mitigate the latency of larger table lookups. These tricks that people know. Banking and other tricks. Local history is hard, but it can be done. There's literature about how to do it. It's all not very good stuff that you see in the literature, but there are ways, clever ways to implement local history if you manage your expectations of what you can get out of it. What else? Okay, so I guess that was it. I hope I didn't go over time.
We're ahead of schedule.
Okay.
Thank you.
Yeah, good.